Welcome back, students. Let's go back to section 3, Fulmer's method. This time, let's do an example problem that is really geared up for Fulmer's method. Previously, we did a 2x2 case, which could have been done through traditional Laplace inversion method because the inverse matrix computation is not that bad. This time, we're kind of stuck with Fulmer's method because the inverse matrix computation is going to be another huge pain in the rear end that we want to avoid. So let's use Fulmer's method to avoid it. Okay, let's do it this way. Okay, let's get the characteristic polynomial and find out all those zeros from there. So Si minus A is the computation we have to do. And what is Si? It's this matrix. Okay, so that's 0, 0, 0, 0. Okay, this is Si, and this is minus A, good. Let's multiply S here to each term, then this is what I'm going to get. Times 0 will not change anything, so we have multiplication only to principal diagonal. So that's Si. And subtract, so what do you have? S minus 1. 0 minus 1/2, so sign change. 0 minus that, so sign change. S minus 1. 0 minus that, so sign change. Sign change, and I have S minus 1. Okay, there you go. So basically we have sign change everywhere, and we have S in the principal diagonal. Now let's take the determinant. Let's take the determinant of this. And then let's take the determinant. Now, how do you find the determinant of the 3x3 matrix? One way to do that is to use, let me see, this method. Go to lesson 13b. Yes, this formula, which is coming from this crisscross. Positive direction, negative direction, we could do it this way. Another way is to take a row and then get number, number, number with alternating sign and take the deleted matrix. If I selected 1, 1, I have to remove first and then first column where the A11 is located. Take what's left, and this is called the deleted matrix, and then find out that determinant, AD minus BC. For A12, select this. So first row out, and first column is also out, and what's left is this matrix, deleted matrix, and then we use that crisscross to find out the determinant. And finally, third one here, and we delete the first row where this A13 belongs to, and then third column. What's left is this matrix here, and take the determinant of that, the AD minus BC, crisscross. We can do it the other way. The second method is a little bit more general, and this is usually the textbook's method than this one. In solution 2, I use this one, so let's do it this way. By the way, this method can be generalized into 4x4, 5x5, whatever. So this one is a little bit more general. That's the method I'm going to select here. Okay, so how does it work? S minus 1 is my first entry, and then the determinant of AD minus BC, S minus 1, 1, negative 1/2, and then S minus 1. Basically, remove the first row and the first column, and what's left here is the determinant that we are looking for. And that's only the first. Now let's move on to next one. We need sign change. So alternating sign. And then determinant of now the deleted matrix. I have to remove the first row and also first column because it came from here. First row, second column. So what's left is -1 and then 1, 0, and s minus 1. Because I removed the first row and the first column, what's left will be -1, 1, 0, s minus 1. Are you with me here? Next, I have to go here. So 0 times, so I don't really have to do anything here, but just for exercise sake, I'll do that. 0. So first row out, third column out. So what's left is this matrix here. So that's the deleted matrix that we are going to have to consider. But actually, why would anybody bother with 0 times something? So I just did it just for instructional purpose. That is not really necessary part. Nobody will actually do 0 times part, this part. Let me de-emphasize that in gray. Okay, how about the others? All right, let's do that. S minus 1, and then we have to do it this way, AD minus BC. So S minus 1 squared. Now. And then the other way around, so plus 1/2 looks like that's what I'm getting. Next, 1/2, and then AD minus BC, so this times that. So negative of S minus 1 squared and minus BC, oh that's 0, so we get this. So crisscross, this -1 times S minus 1, we got that, and then minus 1 times 0, so no problem there. So looks like we can simplify this a little bit. Let's see. We have too many negatives, so I can change these into positive. Plus plus. Actually, I made a mistake here. Let's go back here. Let's do this again. -1 times S minus 1 is not S minus 1 squared. Sorry about that. That should go away. And then this minus 0, okay. Crisscross, AD, negative S minus 1, and minus BC, that's 0. Okay. Oop. And then let's take separate new line to do this computation. S minus 1, S minus 1 total quantity squared plus 1/2. And then I have too many negatives, so plus 1/2 S minus 1. That's it, isn't it? That's it, isn't it? Plus plus. Looks like I can factor S minus 1 out. S minus 1. And then add up this and that. So we get S minus 1 total quantity squared plus 1/2 and plus another 1/2. So do you see that this is just 1? Okay, looks like the factorization and everything is complete. And then we have appropriate eigenvalues. Set this one equal to 0. I'm going to get S is equal to 1. We get the eigenvalues. From the first factor, which I'm highlighting in red, I get S minus 1. And then from the second factor cluster here, which is quadratically reducible, I can rewrite it as S equals to 1 plus I can write like this. Set it equal to 0, and I can do it like that in complex numbers. And then as for the eigenfunctions are, from here I'm gonna get e to the 1t, lambda value is 1, so that's my red, that corresponds to s equals to 1, and this one is gonna be e to the t power cosine of t, e to the t power sine of t. It's better this way than getting complex values and then having to get those back to real later on. Okay, I guess the first step is done. Well, maybe one more. We got all these eigenfunctions, so one more. E to the a t power is therefore m1 and then times 1. Okay, let's put 1 on the left hand side here just for the looks. And then e t cosine of t m2 plus e t sine of t. Okay, let's write like this. If we have scalar function, it doesn't matter if I put left or right, because this is not matrix multiplication, this is scalar multiplication, so it doesn't matter. But if I have just 1, I don't want to put it in the right hand side, so I switch the order a little bit. Anyway, we have the matrix coefficient m1, m2, and m3, and these eigenfunctions, constant 1 and e to the t cosine of t and e to the t sine of t, and we have all those. And the next step will be to determine m1, m2, and m3. So that's step 1. Oops. Are you happy with this? This is my matrix. And then Si minus A. Calculate that. And then determinant of that, which we call the characteristic polynomial. And then the determinant computation of this 3 by 3 matrix. I did it hard way. And take the first entry and then minus second entry and plus third entry in the first row. We have to have this alternating sign. And then the determinant of the deleted matrices. So first row, first column gone, and what's left is that matrix. Here, first row and second column gone, and what's left is this deleted matrix. And finally, here, 0. First row and third column gone, what's left is this deleted matrix, but that didn't really matter because we have to multiply by 0. So we have these two. And then some brute force computation about the determinants of 2 by 2, crisscross AD minus BC. And then please note that S minus 1 is common, so factor it out, simplify, we end up with this kind of factorization. So we have one eigenvalue that comes from the first factor, S minus 1, so S equals to 1, so e to the t power. Now, from this quadratically reducible, you can get e to the t cosine of t and e to the t sine of t. You can easily see those from the Laplace table in page 123 of our textbook. If you have 1 or s over s minus a squared plus b squared, that's that form. Anyway, we have those eigenfunctions, and then 1 e to the t cosine of t and e to the sine of t. We have those three. So we have coefficient matrices m1, m2, m3, and those three we have to determine. How are we going to do that? Plug in t equal to 0, and then take the derivative and plug in t equal to 0, and then take the second derivative and plug in t equal to 0. And those computations are going to be, what can I say? It's going to be a little bit tedious because we have to product rule here, another product rule there, so the derivative computation is expected to be a bit messy. And I'm kind of running out of time, so let me take a shortcut. Let me open up my notebook, show you the answer key, and then go from there. Let's see. Coefficient matrices. Okay, coefficient matrices. How do we deal with those? We got ODEs. So original, first derivative, and the second derivative. And the derivatives were done through the product rule computation. And if you're unsure about those computations, here's a derivation actually. Original and product rule computation and then simplification. Product rule computation and then simplification. And that's the derivation. And that's how we ended up with these three equations. First is straightforward. The second is coming from derivative computation and simplification. And the third, more derivative computation and the simplification. So let's accept all these, and we have this system. And then let's plug in t equal to 0. T equal to 0 to the first, and that's easy. Sine of t part is 0, so that drops out. And cosine of 0 is 1. E to the 0 is 1, so that all drops out. And e to the t power is also 1, so I have just I equals m1 plus m2. That's easy. Next, plug in t equal to 0 here, so sine part is 0, so that all drops out, 0. Cosine of t is 1, so go away. E to the t power is 1, so that goes away. So all these drop out. And e to the t power is 0, so m1 plus m2 plus m3, we get that. Likewise, plug in t equal to 0. Sine of 0 is 0, so it all drops out. And cosine of t is 1. E to the t is 1, so they all go away. And e to the t power is also 1, so we have m1 plus 2m3, so we have this. Now, solving this system of linear equations is actually tedious work. We have three unknowns, m1, m2, m3, and then the others are considered as known. I and a squared are known. We can calculate those later. And you do appropriate computation. Well, here we go. Some substitution and elimination, basically. Assuming you did all those, you're going to get this. Okay? All right. I skipped a lot of tedious steps. And then calculate, we're going to get m1 is this, m2 is this, and m3 is that. Again, a lot of elementary, tedious computation. So a squared minus 2a plus 2i minus a squared plus 2a minus I. Here, a minus I. All right, we have all those. So the conclusion, okay, let's go to the conclusion now. We calculated all those, so put those in, and then there you go. M1, M2, M3, actually, oh, excuse me, this is a mistake. This should not be 1. Sorry about that. If this had been just in class, somebody must have caught it. It's not 1 e to the t power. S is not 0. When s is 0, we have 1 e to the t power. So plug all those in, do my computation, and here's the answer. At least I found the answer. I found the mistake in time and corrected it in time. That completes the problem.